This video is all about factors that will affect the rate of the reaction. So basically it's a little bit of memory work for you guys to do, but I'm going to go through each factor in a little bit more detail. So there are 5 factors that you need to know that will affect how fast a reaction happens. So here they are listed here. The chemical nature of the reactants, the concentration, their temperature, the presence of a catalyst, and the surface area. So we're going to go through each one of those factors individually and in a little bit more detail, and then hopefully you'll be able to understand a little bit more about reactions and their rates. So the first one is chemical nature of reactants. So firstly, similar elements, such as those in the same group of the periodic table, tend to react similarly but at different rates. This type of reaction that metals undergo with oxygen is similar, but here are some other examples. So metals, like sodium and potassium, are so reactive that they are never found as elements in nature. Okay, I'm sure you guys have seen what happens if these elements get dropped in water. They actually will also react with oxygen, sort of in a similar manner, but they're very, very reactive. So we never see them in their metal form in nature. We have to chemically make them because basically they will just react and form a compound if they exist like that in nature. But then there are other metals, such as gold and silver, that are very, very slow to react, or that are just very stable on their own. And that's why we use things, metals like this for things like jewelry and precious objects, because they don't tend to react with water or oxygen or anything like that. So depending on the actual nature of the reactants, what chemical family they're in, if they're reactive or a non-reactive metal, that itself will actually affect the rate of the reaction. So something like silver, we all know that silver will react with oxygen and tarnish, but we also know that that's a very slow reaction, whereas other metals will rust or oxidize a lot faster. So just the metal itself or the nature of the reactant itself can definitely affect the rate of the reaction. The second one is a concentration of reactants. Hopefully this is pretty self-explanatory. If you have a high initial concentration of the reactant, you have a higher rate of reaction. If you have a lower concentration of reactants, if you have less reactant, then the overall rate of reaction will be smaller. And then temperature, hopefully you guys also realize if you increase the temperature of a reaction, the rate of the reaction is also increased. So this shouldn't be too new for you guys. So I'm not spending too much more time on these, but here's a quick example if you'd like. The metabolic rates of reptiles change in response to their temperature of their surroundings. So when it's really, really hot out, their metabolism speeds up. When it's cooler out, their metabolism slows down. So that's sort of a real life example. Presence of a catalyst. So a catalyst, I'm sure you all know at this point, is a substance that alters the rate of a chemical reaction, but it is not permanently changed itself. It's not actually a part of the reaction. Most of the catalysts that we know of have all been discovered by trial and error. So, for example, chlorophyll is a natural catalyst that's required for photosynthesis. Powdered platinum, or palladium in catalytic converters in engines convert car exhaust into less harmful gases. So you don't need to know all these details here, but your catalytic converter is basically something that uses these powdered metals to convert harmful gases that are here into less harmful gases that are actually released out into the environment. So there are 2 examples of how catalysts change the rate of a reaction in everyday life. Okay. Surface area is the last one. So the amount of exposed surface area will affect the reaction rate. So here, the reaction rate increases with the increase in particles. So you can see in my first diagram here, I have a big square. In the second diagram, I've cut that square into 4 sort of smaller squares. Okay, and you can see that the amount of surface area has increased. So if I mash something up into smaller particles, I actually increase the surface area, which will increase the rate of the reaction. So in my first diagram here, I only really have 18 of these particles around my square, whereas in my second diagram, I have 40 little circles around each square, and obviously that, if I can get molecules to touch and collide, then my surface area is obviously increased, and that increases the rate of the reaction. So here's just a further explanation of my picture here. One large piece has only 18 opportunities for chemical reactions to occur, but 4 smaller pieces have 40 opportunities for that same reaction to occur. Okay, now we're just going to look at the collision theory and rate of a reaction, because how things collide will actually affect the rate of the reaction. And we looked a little bit at this in Unit 1, so now we're going to look at it in a little bit more detail. So here is the collision theory. The rates of the reaction can be explained with the collision theory. Here are the concepts that you guys need to know. Particles are always in constant motion at speed proportional to the temperature of the sample. So obviously if you have a higher temperature, molecules are going to move around faster because they have more energy. Chemical reactions must involve collisions of particles with each other and with the walls of the container. The collisions are necessary so that those bonds can be rearranged and new things can be formed. An effective collision is basically any collision that has sufficient energy, so lots of energy, and the correct orientation for bonds to be broken and new bonds to form. An ineffective collision, the particles will rebound from that collision essentially unchanged, so there's not enough energy or they're not in the right orientation. So the rate of a reaction will ultimately depend on the frequency of collisions and the fraction of collisions that are effective. So we need to have lots and lots of collisions, and we need to have effective collisions in order to increase the rate of a reaction. Activation energy. This is probably a little bit of a new concept for you. This is a minimum increase in potential energy of a system required for molecules to rearrange their structure and result in an effective collision. So it's sort of that minimum amount of energy you need to make a reaction go. So think of it as rolling this boulder off the cliff. You need to push it a little bit and add a little bit more energy, and then once you've added enough energy and gotten it to the edge of the cliff, it will roll down and happen on its own. So that's the same thing as what's happening in this potential energy diagram. You have a starting substance over here. In order to actually get it to react and make your products, you have to give it a little bit of energy to start off. So that energy there is what's here, and then once you get that minimum amount of energy, your products will be made. This amount of energy here that's required, that difference there, that's what your activation energy is called. Okay, correct orientation. Particles must also collide with the correct orientation for the collision to be effective. So here is an example. Here's a reaction where you have hydrofluoric acid and chloromethane reacting, and what will actually happen is the fluorine will come here and bond to this carbon, and then this bond here for the chlorine will boot off, and that's how basically a substitution reaction works. Okay? However, if these molecules collide this way, so if instead of the fluorine actually hitting the carbon so it can make a bond with carbon, if the fluorine comes this way and hits the chlorine instead, well, that's not an effective collision, and it's basically just going to bounce back with no reaction. So there's an example of how the orientation has to be correct in order for the reaction to occur. So here's another very simple diagram. In order, if A here is coming in this way and needs to bond to the green circle C, then what will happen is as this bond here is forming between A and C, the bond between A and B is breaking. And then you end up with your products, okay? So you'll end up with your products of A and C bonding together and B all by itself. But if it's colliding this way, you clearly will not end up with these products here, okay, because of the way it's oriented. In order for that to happen, the A has to come in from this side and bond to that B little molecule there. Oh dear, my battery's gonna die. Okay, let's see if we can get through this. Transition state theory is one of the last things I think I need to talk to you guys about. So I've said this before, activation energy is the minimum energy required for that reaction to occur. It's the difference between the initial energy of the reactants and the energy of the activated complex in that potential energy diagram. Here's your definition of an activated complex. It's an unstable molecule containing partially broken and partially formed bonds. So that's what I tried to show you in that A, B, and C diagram on the last slide. And then the transition state, the energy maximum where the activated complex is formed, and then the reaction will actually proceed. So here are potential energy diagrams, okay? You can see here that you start off with certain reactants. You need to give it a certain amount of energy. That's your activation energy to get up to that top there. Once it hits there, it's going to go and make its products, which is good. And at the top there, that's its transition state, where bonds are partially broken and partially formed. Check out these two yellow graphs on the side. The top one is an exothermic reaction, okay, which means that the energy of the reactants is higher than the energy of the products, and that difference in energy here is the energy that is released, okay? The second graph shows an endothermic reaction, so you can see the reactants have less energy than the products, so we need to add in and absorb this amount of energy, plus more for the activation energy, to actually get this reaction to occur. I'm going to stop there for today, and we'll talk about Maxwell-Boltzmann distributions on the next video.